Hello people, what's up? So let's try something new and let's go into chemistry. So today we will start by the basic concept of chemistry, that is atomic structure. Now let us talk about atomic. Before we talk about atomic structure, it is very important to understand how the atomic structure came into being, because the whole chemistry that evolves is from a long time. So we will decide, or we will talk about the history of atomic structure starting from a very late kind of era around 400 BC. And 400 BC, a Indian sage, whatever you want to call him, a Maharishi Maharishi Kannad, proposed a very fundamental kind of thing. He proposed that if there is an atom, like if there is a matter, let's say we have a matter like this, then this matter can be further broken down into another two pieces like these, and these two can be further broken down into another 8 pieces, right? We can further broken down into 8 pieces. When we start to break down all these pieces, we will arrive at a fundamental particle which is naked to the human eye, but this fundamental particle he called it as Anu, and another subdivision can be done, and that will be called the Parmanu. Right? So what he wanted to tell us, that what we know as the atom today was he called as the Anu, and what we know as the subatomic particle was called the Parmanu. So in the 400 BC, Indian and Greek philosophers have already put forward the proposed atomic theory in their being. But the first atomic theory which gave us a scientific basis, the first scientific basis of the atomic theory was given by John Dalton. Well, John Dalton was a British school teacher in the 1808, and in that time only he gave his Dalton's atomic theory. So Dalton's atomic theory. Now, Dalton's atomic theory at that time was considered to be a great success, because Dalton's atomic theory could explain a lot of scientific phenomena involving atoms. Now, the Dalton's atomic theory had a few points or a few postulates that were put forward. Right? It was around 2 centuries old, but still remains valid in the modern chemical thought. The first point, which I would read out, is that all matter is made up of atoms. Matter is made up of atoms, and atoms are indivisible and indestructible. So if we have an atom like this, then we cannot further break down it and neither destroy it by any force or any energy. In the second point, he tells us that all atoms of a given element are identical in mass and properties. This means if I have an element, say hydrogen, then in the hydrogen element has an atom like this, right? Then another atom like this can't be of hydrogen. This can't be hydrogen. For the hydrogen, the atom must be like this, and that is very important. Therefore, they should be identical in both its mass m and all its properties. Then he proposed that the compounds are formed by the combination of two or more different kind of atoms. So for example, let us suppose we have a compound, say water, and we know by our daily common sense or our daily meetings with science that this compound is H2O, and we can understand that it is formed by the combination of two elements, that is hydrogen and oxygen. So that is what is said, that compounds are formed by the combination of two or more different kind of atoms. In the fourth point, he explains us that the chemical reaction is the rearrangement of atoms. So what is if I write H2 plus O gives us H2O, right? So what actually happening here is that this H can be written as H and H, and I will write half of O2, and this is another oxygen molecule, and these three are getting rearranged. These three are getting rearranged into a compound called H2O, which we know as water. Right. So this is what is happening here. So this point is also valid, that a chemical reaction is a rearrangement of atoms. But what actually happened here is after the few years, after 1808, in that time, the model, or what we call as the Dalton's atomic theory, was started to degrade because a lot of scientific experiments came upon us. The first of the scientific experiments which came upon us is the experiment by J.J. Thomson. J.J. Thomson was the first scientist who discovered electrons, and he discovered electrons in 1897. That was around, you can say, 89 years later to the atomic theory, and he found out using a cathode ray experiment that there exists a subatomic particle called electrons. So what actually happened here was that in 1830, Michael Faraday showed us that if electricity is passed to a solution of electrolyte, so what he actually did, Michael Faraday, that he took electrolyte and he put two electrodes in it. Right. So what actually happening here is there's a liquid inside, and he put two electrodes to it, and these two electrodes were connected to a battery or a cell. So this is a positive end, this is a negative end, and thus electrons starts to flow to it. So what actually happened here is when he saw that electricity passed to the solution of the electrolyte, chemical reactions occurred with the electrodes. For example, if this solution was of around ZnSO4 and these electrodes are of Zn and copper, then certain kind of chemical reactions start to take place on the electrodes, which included the liberation and a deposition of matter at the electrodes. So using this, he tried to prove the particular nature of electricity. That is, the electricity is not flow in total packets or in total continuous flow of energy, but it is in a particular nature of electricity. Then another brief discussion that came to us that if the particular nature of electricity exists, then there will be a charge system. And if this charge system exists, then like charges must repel each other and unlike charges must attract each other. In the mid-1850s, many scientists in Faraday began to study electrical discharge. So what actually is electrical discharge? Now let us suppose that we have a big box like this, right? And what we do is, instead of being an electrolyte, we take the air as an electrolyte. So we have an electrode here and an electrode here, and this being, let's say, a gas or a vacuum, whatever you want to be here, high voltage electricity will pass through it. So these were connected to high voltage batteries like this, and high voltage electricity will pass through it. So what happened here was that if there is any particle nature of electricity, then the particle must flow from the cathode to anode. But there was no physical connection between these two particles. Therefore, the main result that should have come out was that there should no current flowing. But instead there was a current flowing, and this was known as the electrical discharge. In partially evacuated tubes known as cathode ray discharge tubes, these kind of experiments were done. So what was happening here was that when scientists tried to pass electricity through it, a stream of rays started to pass from the anode to the cathode. From the cathode to the anode, sorry. So what is the cathode? The cathode is the negative electrode, the negative part of the both terminals. Therefore, if this is connected to the negative, then this must be negative here. So the negative terminal became this one, and the positive was this one. So what actually was happening here was that if we consider, let's say, this, then certain rays are passing like this, right? Certain rays started to pass like this through the evacuated tube. The flow of the current from the cathode to anode was further checked by making hole in the anode. This was done like if this is a perforated plate. A perforated plate means that there are holes in the plate. Therefore, the cathode rays were passed through it, and when the cathode rays were passed through it, they tried to hit at the back. And at this back, there was a small fluorescent coating over there. So when the cathode ray hit on the cloth, they started to glow. So this gave us the result that the cathode ray are emerging and they are hitting the anode at the same time. Now, the results of these experiments were summarized then. The results were summarized that there are certain kind of rays which emerge from the anode. These are the anode. Emerges from the cathode and hits the positively charged anode. Right? And then these rays are not visible, but they can be observed using specific kind of materials like fluorescent or phosphorescent light. Then a certain kind of inferences were taken, like physical properties were taken of these. And the physical properties, they were first like in the absence of electrical or magnetic field, the rays travel in straight lines. Therefore, these were not bended or deviated by any kind of external forces unless they were electrical or magnetic fields. In the presence of electrical magnetic fields, the behavior of the cathode ray was similar to expected from negatively charged particles. Like, for example, if I apply, let's say, I apply some kind of magnetic field, electric field in this direction, like here and here, right? And what I do, I put this as positive and put this as negative. Then what happened was in the experiment that these cathode ray tube started to move upwards. Okay, so that showed us that they were expected to be negatively charged particles, and suggesting that cathode ray consists of negatively charged particles called electrons. Also, the characteristic of the cathode rays or these electrons do not depend upon the material of electrodes and the nature of the gas present in the cathode ray tubes. Therefore, using this specific what we call inferences, it was said that these electrons must be a part of the gas which is present in it, and therefore these electrons were constitute of the atom.